and gentlemen, good morning. I'm Archal Shah from Composites tomorrow. Well, in this interaction, we would try and explore the process of metal deposition on composites. My presentation would take you through the following sections. Why in the world do we need such a metal coating process? The applications of metal deposition. How do we do it? The very science of vacuum sputtering. How do we convert this science into engineering? Well, the nitty-gritties of setup and challenges. And finally, we wrap it up with qualifications and conclusions. The human race has dwelled the globe for a long time, and many intellectuals would divide this journey based on man's romance with the material. The early 3.5 million years, we call it Stone Age. Yes, stone, the very naturally basic available element. We use stone to do everything, to build our homes, to get tools and tackles, for weapons, anything. It was stone. Gradually, man learned how to smelt copper into bronze, which welcomed the Bronze Age. Bronze started replacing stone from almost everywhere. And gradually, we further learned processing iron and steel, which is when the Iron Age started. People like you and me would love to call this age as Carbon Age. Yes, Carbon Age. An age where we manufactured materials by combination of two or more materials, and the outcome material would have a completely different properties to that of the combining materials. That's the very basic definition of composites. Now the idea is, if we make a deposition of thin metallic layer on this composites, would it add an extra dimension to the engineering application of this composites? Let's find it out. A typical application, in my view, would be solar mirrors. A huge solar mirror with a coating of silver or aluminium. It would be a lighter one and reflectivity of a plain mirror. There was a concept of using solar mirror in space to manage the climate change. Maybe we will be nearer to resolving that or to using that concept. The second application could be orthopedics. Carbon fiber has already made an entry into orthopedics. Being lighter in weight and having higher strength has qualified them for a lot of applications. If these are plated with gold, they will provide an excellent jump resistance. Whosoever has interest in defense, in today's generation, they would have heard the word called stealth technology. We want our missiles that are stealth, we want our aircrafts that are stealth, our submarines to be stealth, and whatnot. And we all know carbon fiber has an excellent property of absorbing electromagnetic radiation. But every platform or equipment has electronic items on it, and these are the source of electromagnetic wave. What if this same wave becomes the source for the enemy radar? What if we can conceal this electromagnetic radiation within this shell itself? We will be inching towards a more stealthier platform. We can also use it for coating on satellite panels, and even we can go forward and do the coating on packaging for superconductors, a typical titanium coating on carbon fiber. I think sky is the limit to the application of metal deposition on composites. Let's take a case so that we can understand this in a better detail. We in this case would like to coat a shell, a carbon fiber shell, such that if there is an incident radiation, there would be a localized heating, and it will also be a source of electromagnetic signal. We want the coating such that these rays are reflected internally as shown in the animation, and heat is conducted? Well, clearly, we require something that is optically reflective and thermally conductive. What can better be than aluminium? A coating of aluminium with mirror-like reflectivity would be a handy solution for this. So let's explore the science of coating. The basic process of coating aluminium that we propose here is vacuum sputtering. Vacuum sputtering is physical vapor deposition process done at room temperature. Well, let's imagine there is a closed chamber. We put a carbon fiber shell inside this chamber, and whatever metal we want to coat it with, in this case aluminium, so we put aluminium as the central target. Now, let's fill this entire chamber with plasma. Let's simulate the plasma. What is plasma? Basically positive ions. And whenever we give a negative charge to this target, it attracts a positive ion which bombards it with full force, displacing the base metal and allowing it to deposit on the substrate, which will be composites, as shown in the animation over here. Exactly. But it is more simply said than done. Well, let's dive slightly more deeper to understand this process. The same chamber with carbon fiber shells, aluminium target, the blue circles over here are resemblance of the air molecules. We all know Avogadro's law. A typical 22.5 liter will have 10 raised to 23 such air molecules. As soon as we switch on a vacuum pump and we take it to 10 raised to minus 3 millibar of vacuum, it sucks a lot of air molecules. How much? 1 million molecules in the same 22 liters. Well, if we take it to 10 raised to minus 6 millibar, it would further suck some more molecules. Again, how much? 1 billion molecules in 22 liters. But there is an addition. A lot of molecules that are affiniated, that are stuck to the surface of chamber, will also be affected because of this vacuum, and it will create a space-like situation. This is when we inoculate our chamber with argon gas. This sprays a lot of argon ions in the chamber, increasing the availability of argon ions per mole of this gas. Now, as soon as we ionize, that is, give a potential difference between the target and chamber, the immediate effect would be ionization of argon. Well, the electrons from the outermost orbit of the atom will get excited, and when they come back in the resident orbit, they will emit photons. These photons are source of light which you see through your sputtering windows, color of plasma. Well, as soon as that happens, due to the negative charge of target, these ions are attracted towards the target and bombarded. This bombardment creates the displacement of basic aluminium atoms from the target to the substrate, thus coating the substrate. But we can increase the efficiency of this deposition process. Let's say if we introduce a magnetron assembly at the center, a typical magnetron assembly with the electrode coils like a solenoid, whenever a magnetic field is created by Lorentz law, there will be a perpendicular electric field. And what will happen by that? This will attract the positively charged argon ions towards the central target. Thus, the probability of striking the ion to target increases, and hence the deposition becomes more efficient and uniform, as shown in this figure. Well, this is the central idea of using vacuum sputtering for depositing metals on carbon fiber composites. Now, let's say if we want to set up a facility, how does it look like? The first and foremost thing for such a facility would be a dust controlled room. It should have at least class 10 temperature and humidity control, and the basic level of illumination is must. Other than that, we would require a steel chamber. It would be preferred to have polished stainless steel with a viewing window so that the process can be monitored manually also. And we would require a very high vacuum capability pumps. This can be a system of auxiliary and turbo pumps that can make us reach from the atmospheric pressure to 10 raised to minus 3 millibar and thereafter to 10 raised to minus 6 millibar. We would also require a magnetron assembly that can oscillate. Why oscillation? Well, generally, due to the additional affinity or additional charge created by the magnetic field, what would happen is the efficiency of reaction near the magnets would increase inadvertently, having a higher coating ratio near the magnets and the earth space is a bit left out. This is where we require the oscillation. This oscillation will spread the coating and have a more uniform outcome. This is one of the most complex system of the entire vacuum sputtering. The heart of vacuum sputtering would be this. Well, the entire process also requires a continuous cooling arrangement because of the heating that happens due to the presence of electromagnetic field. So we require a dedicated water-based chiller plant and of course a control panel because one may not be able to go run around the processes to switch on and switch off. That is where basic panel that can attune a process in a sequential way. All said and done, even after equipping ourselves with all these facilities, we are not good to take off. Yes, there may be a few challenges that we may need to overcome during the process. The very first that I envisage is degassing. What is degassing? Well, we all know about vapor pressure, or maybe the video here shows it. But all our composites, even the monolithic composites, will have resins, and at 10 raised to minus 6 millibar, to maintain the vapor pressure, the resin will continuously try to emit gas, which will be collected as the gas of the system and impeding our process of sputtering. This process gets multiplied with the sandwich composites because there will be either a polyurethane foam or a different variety of core, but absolutely there will be another member of plastic which will be emitting gas. And if we are using any sealants for edge sealing, glues for bonding, rest assured they are going to play their part in making your life troublesome. But of course we are there to relieve you from troubles. And the solution to degassing? Simple. Before putting your product in the sputtering tank, it is advisable to have a separate degassing chamber. You take it to, let's say, 85 degrees centigrade at 10 raised to minus 3 millibar vacuum, and you have a shell that is already degassed at 30 minutes and ready for sputtering. Well, the second problem that one might face is the uniformity of coating. Most of the people find it difficult to coat things uniformly, especially there will be higher deposition, as I said, near the areas of magnet, and there will be black shades around. How do we deal with this? Well, the solution is exactly the same thing. Make your magnetron assembly moving in such a way that your uniformity enhances. The design of target and movement of magnetron is the heart of vacuum sputtering process. The next difficulty that one may face with this process is reflectivity of the surfaces. In many cases, you require vacuum sputtering to enhance the reflectivity of carbon fiber composites, typically a black component. So, and how do you do that? Well, a sublayer of vacuum, the sublayer of varnish, not any varnish, a varnish that can be stable at around 100-110 degrees centigrade, and a varnish that is sprayed by atomizing so that you have a very uniform layer of varnish. The reflectivity or the uniformity of varnish is the one that will ensure the uniformity of the outcome process of vacuum sputtering. This has to be done in a very zealful manner. Well, certain other difficulty that one might face is affinity with metals. Seldom we want to coat a composite that has either a metallic insert or it has a co-bonded product with metal. And metal has this uncanny way of romancing with ions. And we have to play our roles of breaking the romance by maybe putting a plastic lead on those metals. Yes, a simple suggestion of putting a plastic lead, covering them, wrapping them, will break the affinity between metals and the ions, and thus there will be a uniform deposition of the ions, even at the areas where the metal bonding is there. And the last, I think, one of the important but the last challenges that we may face is oxidation of target. Most of the times, the team that does sputtering does it successfully the first time, the second time, the third time, it doesn't sputter at all. The vacuum is achieved, plasma is generated, but sputtering doesn't happen. Yes, that happens at times. And why? The reason being, most of the times you want to do a coat of metal on composites, and this coat has to be of a very pure metal. In case of aluminium, 99.95% pure aluminium. And what happens when we put this aluminium in open atmosphere? Well, it will become aluminium oxide, and aluminium oxide will not go anywhere. You bombard it, but it will not sputter its ion on carbon. So, the idea is to remove or to reverse the oxidation process. In case of aluminium, you can just dip the target in caustic soda bath and it's good to go. And same can be with the other processes. And this brings us to the last lap of the presentation. Having sputtered the shell, having the wonderful coating around, how do I determine if my coating is successful? Do I measure the thickness? I would not suggest so. Reason, the thickness measurement technique is still not developed completely and may misguide you a bit. Plus, there is always a variation because this is just a nano thickness built up. The better way of checking will be a functional check. As example, you have done a coating for emissivity or reflectivity. Take a black body, put an emissimeter, check its emissivity. Take a white body, put an emissimeter, check it, and now, having calibrated it, check it on your substrate. It should have the requisite level of reflectivity, most of the times 90 to 95%. Well, if you are doing it for electrical conductivity, measure the resistance, but do it functionally. Other than functional test, yes, one can run a visual check in which you try to identify if there is a black spot, an anomaly, non-uniform coating, yes. And at the end, one must try and do an adhesion check. A simple adhesion check, put a tip with a standard tackiness and adhesive bonding and try to pin it off. The coating should not come off with the tape. And that's it. Your sputtered shell is good to go. You pass the test. This is all from my side on vacuum sputtering method for deposition of metals on composites. I am sure you guys enjoyed the presentation. Thank you very much for listening to this.